A triangle is the simplest shape, but hidden on the inside, concealed from your vision, lie many secrets we're going to expose today. So, there's many ways to calculate the area of a triangle. Half times base times height is the simplest one and is the most common way to find the area of a triangle. And this is proved by, of course, taking the outside rectangle and seeing that it's half of each part is half of the rectangle, because half 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 half. But this is not the only way to find the area of a triangle, because sometimes you won't always have the base and the height. Sometimes the problem will just give you 3 different sides. Now what do you do? How do you find the area of a triangle with 3 sides? The trick? Herons Formula. So what you do is you first find the perimeter, a plus b plus c. That's a perimeter, right? And then you take half of that, and that's what we'd like to call the semi-perimeter, half of the perimeter. A plus b plus c divided by 2. And then what we do is we plug it into this complicated seeming formula, but it's really not that complicated. Basically, it's the square root of the semi-perimeter times the semi-perimeter minus 1, the first side, times the semi-perimeter minus the second side, times the semi-perimeter minus the third side. S times s minus a, s minus b, s minus c. So you can think of there's 4 terms, semi-perimeter and semi-perimeter minus each of the side lengths multiplied together. Let's now try this simple but interesting example that uses multiple triangle area formulas that we just learned. Given that the heights of triangle A, B, C have lengths 15/7, 5, and 3. Okay, so A, B, C, and we're given that their heights, which is the altitudes, right? Heights form a 90-degree angle with their base. So something like that. That's going to be a height of the triangle. That, and then something like this as well. And also, we could also have a height that's like this. All of these 3 are different heights. There's 3 heights because heights form a 90-degree angle with their base. There's 3 sides, so each of their sides have their own heights. And they have lengths 15/7, 5, and 3. So let's say this is 5, let's say this is 15/7, and let's say this blue one over here is 3. Okay, what is the square of the area of ABC? We know how to find the area if we have base and height, but we don't have any bases here. We know how to find the area if we have 3 sides using Herons Formula. We don't have any sides here. We only have 3 heights. What are we supposed to do with that? We don't know what they are, so the best trick here would be to call them variables. Let's say that this over here, let's call this side length A, this side length B, and this side length C. So now, in terms of these side lengths, let's find the area. Area equals half times base times height. The base is A, so just A, like that. The height is 3, so half base height is half A3. Times 3, of course. Okay, so we found the area in one way, and it's a really good strategy in these types of problems to find area in more than one ways. And this is a key strategy that you'll see recurring throughout many problems, finding area in multiple ways to get information. So we found the area in one way, base, height, right? Can we find it in another way? Try and think about another way to find area. Base, height. Aha! Half times B times 5, because B, 5, their bases and height of the triangle as well. So another way to find area. And there's even a third way. half times c times the height 15/7, right? If we got this base and this height. And these heights always form, of course, 90-degree angles with their base. Okay. So what does this give us? We know all three of these quantities are equal. So what we can do is we can also say that 3a equals 5b equals 15/7c by just multiplying each of these terms by 2, right? We can multiply them all by 2 to get this. So what does this give us? We know 3a equals 5b equals 15/7c. Let's say this is equal to some quantity x. We don't know what it is. Then a, or rather, let's say it's equal to 15x. You'll see why we're going to let it equal to 15x instead of just x in a second. Now we have a is 5x. Yeah, because 3a is 15x, so divided by 3, a is 5x. B is 15x divided by 5, 3x. And c is 15x divided by 15/7, that's 7x. And that's why we did it in terms of 15x. So now we don't have any fractions. Because when we divided by 3, 5, and 15/7, they all gave integer numbers of x. And the reason we do this is now we know the ratio of a to b to c. 5 to 3 to 7. And that's how we converted this condition into this ratio quantity. The trick is, let it be equal to something else, and then express each of these variables in terms of that x to find the ratio. So we know the ratio of side lengths. Now, what does that even help? How does that even help us? A is 5x, B is 3x, and C is 7x. We found the area in 3 ways. Like I mentioned, it's a really good technique. It's going to come up again and again in geometry, finding area in multiple ways. We found it in 3 ways. Is there a fourth? We've got 3 sides in terms of x. We can use Herons Formula. So Herons Formula, remember, we need to find the semi-perimeter, which is 3x plus 5x plus 7x, divided by 2, which is 15x divided by 2. That's S, semi-perimeter. And now we just plug it into Herons Formula. S, which is 15x over 2, times S minus each of the side lengths, and then the square root of all that. So 15x, 15x over 2 minus 3x, 15x over 2 minus 5x, and let's make it a tiny bit smaller so we can fit everything. Whoops. And of course, the last term will be 15 over 2x minus 7x. And now we can rewrite this. 15x over 2, of course, just stays like that. 15x over 2 minus 3x, that's 15x over 2 minus 6x over 2, which is 9x over 2. And 15 over 2x minus 2 minus 5x, that's minus 10x over 2. That's 5x over 2. And minus 7x, which is 14x over 2, that's half x. So half x, or simply x over 2. Now, what is the square root of all that? Okay, so let's move this aside for now. We're already done with this part of the question. The easiest thing to notice here is we can rewrite this as 1 over 2 to the 4, right? Because 2 4 times the square root of this, of course, times x to the 4, because we've got 4 x terms. And then times 15 times 9 times 5. And now, what we can take this, notice how we can rewrite 15 as 5 times 3. 5 times 3. And now we can pair up the two 5s to form 5 squared. And 9 is just 3 squared, right? And the reason we're doing this is so when we take the square root, it's something simple. So what's the square root of 1 over 2 to the 4? Or simply, you can think of it as 1 over 16. The square root of 16 is 4, so 1 over 16 square root is 1 over 4. The square root of x to the 4th is just x squared. And the square root of 3 squared times 5 squared is just 3 times 5. Because, right, 3 squared is square root of 3 squared is 3, 5 squared is 5. And then we've just got the straggling square root of 3 term that's left at the end. So it simplifies to 15 over 4 root 3 times x squared. That is the area, right? We found that using Herons formula. But remember how A is 5x. Remember how this quantity, area, is equal to half of, it's equal to half of 3a, and 3a is equal to 15x. So it's equal to half of 15x. So now what we can do, I'm blocking. Basically what I wrote is that it's equal to half of 15x, as you can see here, because 3a is 15x, and half of 3a is 15x over 2. And we know that these are both representations for area, so we can set them equal. Half 15 over 15x. Or this should be x squared. I think it got deleted. And now we can cancel x from both sides. We can multiply both sides of the equation by 4 to get 15 root 3x equals 30. So x equals 2 over square root of 3. And now it's asking for the square of the area. So now we can simply plug it into one of these expressions for the area. Let's plug it in over here. Half 15x, which is 2 over root 3. And these 2's cancel, so it's just 15 over root 3, which is 15 is 5 times 3. So 5 times 3 over root 3. And 3 over root 3 is just root 3. So 5 root 3 is the area. And it's asking for the square of the area. So we just do 5 root 3 squared to get 25, which is 5 squared times root 3 squared 3 equals 75, which is our answer. So this is a cool problem that basically uses area in multiple ways. First, we use area in multiple ways using half BH to find the ratio of side lengths. Then we plug that into Herons formula to solve for x, which we define to be this quantity here. And then from there, we set those quantities equal because we know they're both expressions for area. We solve for x, and we found the area from that value of x. Okay, now there's another way to find area using in radius. So basically, we say this is an inscribed circle in a triangle if it's touching all 3 sides at exactly 1 point. Then it's an inscribed circle. And the inscribed circle has a radius. We call that the in radius. And we're given that the in radius times the semiperimeter equals the area of the triangle. Now, why is this true? Well, there's a really cool proof. We can essentially divide this into 3 different triangles. So the area of this region over here, let's do that again. The area of this orange region here is going to be half, let's call the side length A, half AR, right? Because half base times height. And this is 90 degrees here. The area of this region here, whoops, let's do that again, is going to be equal to, let's call this side length B, half BR. And this region over here, the final region that keeps happening, is going to be half of the side length of that times the radius. Sorry, it keeps disappearing for some reason. So let's call this C, it's going to be half CR, because the base is C and the height is R. the total area is half AR plus half BR plus half CR, which is just R times half times A plus B plus C. And notice how this is just the semiperimeter, so it's radius times semiperimeter. A really cool proof. And now we're going to explore some special triangles. So before equilateral triangle, let's take a look at 40, 40, 45, 45, 90. So a 45, 45, 90 triangle has two angles 45, one angle 90. If it has two side lengths of length A, its hypotenuse will be root 2 times that, so A root 2. And the area of that triangle is just A times A divided by 2, because A is the height and A is the base. Now we've got another cool triangle called the 30, 60, 90 triangle. And this is a special triangle because the ratio of the shortest side, the shortest leg of the right triangle, to the hypotenuse is half. So the hypotenuse is 2 times longer than the shortest side, the shortest leg of the right triangle. And the longer leg of the right triangle is root 3 times bigger than the short leg of the right triangle. So that's the properties of the 30, 60, 90 triangle. And the area is just A times A root 3 divided by 2. Okay, and now we're going to come back to equilateral triangle. And for equilateral triangle, what we can do is we can draw a line through the middle, and that will divide the 60-degree angle into two 30-degree parts. And now what we essentially have is two 30, 60, 90 triangles. If the hypotenuse is A, then this over here will be A over 2 by 30, 60, 90, this part. And that means the height is 8 times 8 root 2, 8 divided by 2 times root 3, A over 2 times root 3 by 30, 60, 90 properties. So this part is also A over 2, right? So the area of the triangle is now just half base height, which is half A times A over 2 root 3, which gives us this cool looking formula over here, which is good to memorize. Root 3 over 4 times side length squared. That's the area of a equilateral triangle. Okay, now we're ready to move on to Pythagorean Theorem, which states that the hypotenuse squared equals the sum of the two legs squared. So this squared plus this squared equals hypotenuse squared. And I'm not going to show the proof here because it's going to take too much time, but there's some important Pythagorean triples that are good to memorize. And a Pythagorean triple is basically a triple of 3 numbers such that they can form, the side lengths can form a right triangle. For example, 3, 4, 5. 3, 4, 5 is a Pythagorean triple because they form a right triangle since 3 squared plus 4 squared equals 5 squared. Now, some other Pythagorean triples are 5, 12, 13. 5, 12, 13 as well is another common one. 7, 24, 25, 8, 15, 17, 9, 40, 41, 20, 21, 29. Those are the important ones. I suggest you know them. Also, if we have all numbers in a Pythagorean triple multiplied by the constant, it's still a Pythagorean triple. For example, 3, 4, 5, if you multiply by 2, gives 6, 8, 10. And 6, 8, 10 can also be the side lengths of a right triangle as well. 6, 8, 10. And these are helpful to know. Let's now learn some special properties for right triangles. So essentially, if we have a right triangle like this and we draw the altitude to the hypotenuse, we have some cool properties. One of which says that, let's make it blue. We've got this side length times this side length over here equals this side length squared. So BD squared equals AD times DC. And this is true because it's a right triangle and this is the altitude. Another property of right triangles is that this over CD times the whole thing, CD times the whole thing equals BC squared. Also, AD times the whole thing equals AB squared. And you can memorize that by looking at, okay, we're looking on the right, on the right side. It's going to be AB times AB equals this times that. Now, these are not completely necessary to memorize, but they can save you a lot of time. So the reason this is true is because of similar triangles, which we'll learn in a future video. But these properties can definitely save you time in geometry problems. Okay, now we're going to explore medians. So what is a cVian, first of all? A cVian, if you have a triangle, you take this point and you draw a line to, you have a triangle, you take a point, you draw a line to any point on the opposite side. This is called a cVian. Now, cVian can be anything. It can be, if you have a triangle, it could be here, it could be here, it could be here. But there's a very special type of cVian we like to call median. cVian, median, they rhyme. And a median is a line connecting a point to the midpoint. So, like you see over here, P is the midpoint. AP equals PC. These two parts are equal. So this BP is going to be a median. And there's a special property for medians in a right triangle. Right triangles are just really that good, aren't they? They have so many special properties. So because it's a median, we have AP equals PC. And in a right triangle, there's a special property that AP equals PC equals PB as well. All three of these will be equal. Because midpoint condition, these two are equal, and this is equal by something else. And the reason that that's equal is because we can draw a circle. Remember from the previous video, we learned inscribed right triangles? Well, if we draw a circle around it, this is an inscribed right triangle. So that means that it's essentially, if AC is the diameter of the circle, which means that P is the center, and then you can see that these are all radiuses of the circle, which are equal. So that's why this property is true. Let's now move on to a problem that uses this property, or something that uses a similar property. In triangle ABC, the angle trisector of BAC closer to AC than AB. So ABC angle trisector at D, so there's an angle trisector essentially. And given that ABD is equilateral with area 1, compute ABC. So ABD is an equilateral triangle. Let's call it side length X. And it says here that angle trisector BAC. And an angle trisector is just something that divides the angle into three parts. Or in this case, it divides the angle into one part that makes up 1/3 the total angle, and one part that makes up 2/3 of the total angle. So essentially, all that angle trisector means is this part over here will be 1/3 of the total angle, because it's an angle trisector. And the reason we know it's not the opposite, that this is 1/3 of the total angle, is because it says over here that closer to AC than AB. So the angle trisector closer to AC than AB. There's actually going to be two angle trisectors that trisect the angle into three parts, but this one, as you can see, is closer to AC than AB, so it's the one we're going to be considering, not the red one. So, let's just draw it back. So because it's an angle trisector, all three angles here are going to be equal. A. Cool. And now, this line is not really relevant for this problem, so instead we can just see that this angle, the total angle here, is 2A. And this angle is A. But wait, we know ABD is an equilateral triangle. Equilateral triangle means all three angles of it are equal. We know equilateral triangles, all angles are 60 degrees because they're all equal. So that means 60, 60, and this angle is also 60. 2A is 60, so A is 30 degrees. Wow. So this is 30, 2A is 60, and yeah. Okay, now we're given something. ABD has area 1. Compute the area of triangle ABC. Okay. Notice here, all three of these side lengths are equal, right? Specifically, BD is equal to DA. Now, remember what we just learned? And first of all, it's a right angle, right? This 60 plus 30 over here makes 90. In a right triangle, we know that the median has this special property where this is equal to this, right? All three of these parts are equal. And we know that two of these parts are equal, so the third must be equal as well. So this angle over here this side over here must also be equal to x. Because of the property, we know that this is equal to this is equal to this. Because it's a right triangle, and we know that if two of those conditions are true, the third one must be true as well. It can't be anything smaller or bigger, because if it was smaller or bigger, then AD won't be equal to BD. Okay, so now we know the area of this equilateral triangle is 1. This blue thing over there. But we're trying to find the area of the whole thing. Now, a common approach is to use the formula we just learned, root 3 over 4 side squared, and then find the side length and do stuff like that. But here's a simpler solution. Now imagine just rotating this triangle on its hypotenuse. Now, the area of this equilateral triangle is half base, which is x, times height, which is 1. Now the area of triangle ABC is half 2x is the base, and then the height is also just h. So the key idea here was the height of those two triangles is common. So then the ratio of their areas is just the ratio of their bases. So we have half xh is 1, so half of 2xh, this is just going to be double this quantity, right? Because 2x instead of x. That's 2. So our answer is just 2. The key idea here was noticing how the angle trisector meant it was a right triangle. And then from there we saw this is equal to this. Oh, that must mean this angle, this is also equal as well. And then we use the median to hypotenuse property. And then we saw, okay, this is x, and that this is x as well. And then we saw x, h, that's the area of this triangle. x2h, 1/2 x2h, the area of the ABC, the big one. They share the same height along this side, so we just look at the ratio of their bases. And that highlights another key strategy, using all three altitudes to find area. Like, it's not just going to be this times this. That's not the only way to find area. You can use this side as well and this height as well. And that's mainly the key idea here. And there's some other properties, like if we connect all three medians of a triangle, right? Medians are to the midpoint. They'll intersect at this point called the centroid. And the thing about centroid is we know that there's a special property that it's going to be 2/3 of the way down from the median. So this over here is 2/3 the whole median. So this is 2/3 this. And that's true for any triangle, not just equilateral. Any triangle, long, big, short, small, doesn't matter. Centroid is 2/3 of the way down the median. The incenter of a triangle is the intersection of all the different angle bisectors. And that's actually pretty cool because the angle bisector is just something that divides the angle in half. So if you draw all three angle bisectors, they'll intersect at this point over here called the incenter, which is the center of the inscribed circle, which is a circle that touches all three sides of the triangle. And now you can check out all these practice problems to practice what we learned today in the free Mastering AMC book. You can check it out by clicking the link in the description. But we're ready to move on to not 3 sides, but 4-sided shapes, quadrilaterals. We're going to explore some more cool properties of quadrilaterals in the next video. Click on it right there.